Hi, I'm Harman. In this presentation, I'll share our work on sensible AI, which reimagines interpretability and explainability using sense-making theory. With AI and ML-based systems being routinely deployed in the wild, their unchecked use can cause significant harm. We've unfortunately seen several examples of this in both industry and academic settings. To help with this, researchers have designed interpretability approaches that explain model behavior and outputs. These approaches generally fall under two categories. There are glass-box models that are inherently interpretable, like linear models and decision trees. The other approach is post hoc explanations for black box models like neural networks. With both approaches, you can get three common types of explanations. Local explanations, which explain how an individual prediction was made, the relationship between an individual feature and the output variable, and global explanations, which provide a summary of feature importances assigned by the model across all data points. To make these approaches human-centered, researchers have proposed design guidelines inspired by prior work in philosophy, cognitive, and social sciences based on how people explain things to each other. There are some existing tools that operationalize these design guidelines. For example, here's one that provides what-if answers using counterfactuals. We argue that these approaches and tools, even when designed with social science insights in mind, are not going to work. And here's why. So far, I've talked about why we should care about helping people understand ML, what we can do about this problem, and how researchers have designed solutions for this problem. But the important question that we've missed is, where's the who in all this? We're building all these approaches and tools, but we know very little about how people use them. Instead, we propose a shift from improving explanations to understanding how humans make sense of complex and sometimes conflicting information. Here's a high-level conceptualization of the role of explainability, which says that a successful approach helps us answer the following questions about the model. The question that isn't clear in this conceptualization is, what about who the explanations are intended for? To answer this question, we use Weick's sense-making theory to understand relevant factors about how people make sense of something. These include things about the individual and their environmental, social, and organizational contexts, which we have translated for the human-machine setting. I'll provide an overview for each of these properties, and you can read our paper for all the nuances on these. Weick notes that sense-making starts with the sense-maker and what influences their identity. People want to feel positive about themselves, both individually and when they think about their audience. For interpretability, this means that given multiple explanations, people will internalize the ones that support their identity in positive ways. Consider this example where Sharon and Avery both post content to a platform, and some of their posts are flagged for removal. Let's say they're given the same explanation for why this happened. Sharon might think her political affiliation is why her post was removed, whereas Avery might focus on the content type as the explanation. In either case, by focusing on these partial explanations, they can maintain a positive identity and believe that they were not at fault. While the first property considers the influence of audience on identity, the second property explicitly focuses on the varying audience types that a person is surrounded by and their larger social and cultural contexts. For interpretability, this means that differences in micro and macro social contexts affect the effectiveness of explanations. As an example, consider the case when Google tried to launch a tool that predicts diabetic retinopathy based on eye fundus photos. After being able to successfully do so in the US, they tried launching it in Thailand, but did not see positive results. One reason for this was the infrastructure itself. A different cultural context meant that there was more variability in the facilities where the photos were captured, and whether trained technicians were available for performing the fundus exam. Another interesting issue was that patients did not expect quick results. Normally, people would have to wait a while before getting their results. Then, if needed, they would schedule an appointment with a specialist in bigger cities that the patients had to travel to. With getting immediate results, these appointments could be scheduled for the same day, but people did not budget enough time for that travel. Therefore, some of them preferred not to get immediate results. For the third property, Weick notes that sense-making is a reflective process, which requires some time and deliberation. If people are provided additional information before this reflective process can be completed, then they often choose to simply accept the information. For interpretability, this means that providing explanations before people can reflect on the model and its predictions negatively affects sense-making. Consider a radiologist tasked with reading chest radiographs to determine if a patient has COVID-19. They have help from a classification software, which also provides these saliency maps to explain its reasoning. As you can see in these figures, the saliency map highlights regions not only in the lungs, but also lateral markers in the corners as being relevant to the prediction, especially for COVID-19 positive cases. Ideally, the radiologist would see this as a spurious correlation if they spend time reflecting on the radiograph. But with the immediate explanation from the tool, the radiologist might not engage in sense-making at all. For the next property, Weick notes that we do not make sense of an external thing. Rather, we iteratively produce and understand the environment that we and the sense-making object belong to. For interpretability, this means that the order in which explanations are seen affects how people understand a model and its predictions. Consider the case of predictive policing based on historical crime rates and location data. The model's predictions influence both the officer monitoring the software as well as those patrolling. Both will update their environment to be focused on predicted hotspots. Further, when arrests are made using model predictions, they provide additional evidence to the model that the patterns it has identified are accurate. In this way, the feedback loop causes the model to become increasingly biased. Research shows that Black neighborhoods are disproportionately targeted by these predictive policing algorithms. Next, Weick notes that sense-making never starts or stops. It's an ongoing process. As such, interruptions to this ongoing process affect what is understood. This is often how emotion gets involved in sense-making, since interruptions usually have a positive or negative emotional response attached to them. For interpretability, this means that the valence and magnitude of emotion caused by an interruption change what is understood. Consider the predictive policing example again. Let's say an arrest was made and the police officer monitoring the model's predictions has to explain their patrolling assignments. Say their experience with the algorithm has been positive in the past. There's a high likelihood that they'll use the explanation from the algorithm to justify their patrol assignments. Now let's say that they decided to take a break and browse the online news before writing their report. They come across an article where the predictive policing algorithm led to harmful consequences. The ongoing property suggests that this would influence their use of the model and its explanations. The sixth property is about cues. Since people can rarely internalize all available information, what they focus on shapes what is understood. For interpretability, this means that highlighting different parts of explanations can lead to varying understanding of the underlying data and model. Consider a marketing company that uses a machine learning-based software for hiring. The software rates candidate A higher than candidate B and provides explanations for the ratings. The HR folks see that A's rating is based on their facial expressions during the interview. They seem enthusiastic, were smiling, and not visibly nervous. They consider these to be good attributes for a sales representative and hire A even though B is more qualified. All additional information about both A's and B's qualifications is also noted in the local explanations, but might not be the cue that is extracted or focused on. Finally, in this last property, Weick notes that people are never searching for accurate understanding of something. Rather, sense-making is all about a plausible and coherent story. For interpretability, this means that given plausible explanations for a prediction, people are not inclined to search for the accurate one. Consider the example with the radiologist again. Seeing the lung marker here might convince the radiologist that the model is always reasonable, but say that they were not completely convinced and looked at more cases. Now they notice that these lateral markers are also being used. They're still looking for a plausible story though. Perhaps the patient was coughing and could not stay still when the radiograph was being captured. That would explain why there are more lateral markers for a COVID-19 positive patient. In reality, the model is relying on spurious correlations, but with the role of plausibility in sense-making, the radiologist might not try to accurately interpret the saliency maps. Sense-making isn't really a solution for how to understand AI and ML. It simply tells us the properties of human cognition that we need to account for. So how do we do that? Luckily, Weick and his colleagues also provide some direction on this. They observed sense-making in organizations that have successfully avoided catastrophes despite operating in high-risk environments. These are organizations like healthcare and air traffic control systems, naval aircraft carriers, and nuclear power plants. They identified 5 common properties in these high-reliability organizations: a preoccupation with even the smallest signs of failure, a reluctance to simplify any event and always being on the lookout for what's unique about it, a sensitivity to operations and heightened awareness of each human and machine component, a commitment to resilience in the form of incorporating diversity in training and skill sets, and a deference to expertise of the people on the ground who are dealing with low-level details of a situation. Based on these properties, we propose a sensible AI framework for designing reliable AI and ML-based systems. These ideas are intended to complement existing tools by acting as checks and balances. I'll describe them using the example of an AI-based software being used by the HR department of an organization to understand job satisfaction. Again, please read our paper for details on these. The first design idea is themeful design. Instead of trying to make a system seamless for ease of use, themeful design argues for showing complex features and information. In this example, you can see that before someone clicks through to review, the system suggests similar and different profiles and what-if analyses. Strategically placing these within the system is important. Sensible AI also suggests inducing skepticism by questioning explanation outputs every now and then. This is important to keep a check on over-reliance on the software. Here you can see the system questioning the importance assigned by the model to a particular input feature. Our next idea, adversarial design, is all about promoting contestation and dissensus. By designing sensible AI systems with dissensus-centric features, we can increase the likelihood that someone raises a red flag given early signals of a failure. Finally, there's continuous monitoring and feedback. When systems are deployed in real-world settings, changes in data collection and distributional drifts are a given. Continuously monitoring individual and organizational metrics and communicating these across all users can be an important check for ensuring reliable use of these systems. Here you can see some example features that make it easy to do so. I started this presentation with the question, where's the who in all this work on interpretability and explainability? Here's how we answered it. We translated environmental, social, and organizational factors relevant for human cognition from Weick's sensemaking theory to the human-machine context. And we proposed design ideas for sensible AI, which accounts for human cognition. Thank you.